In the last few years, something extraordinary happened. Machines started drafting novels from a brief prompt, solving complex mathematical proofs, creating and debugging full applications, generating research hypotheses, and providing real-time tutoring with personalized explanations. And then someone said, it's just predicting the next word. There's no understanding, no reasoning. It's autocomplete on steroids, a very expensive printer. Maybe you've heard that, and honestly, it's not a stupid thing to say. So is it true? Let's look inside. That is a transformer. The architecture that powers ChatGPT, Gemini, Claude, every major AI system you've heard of. And today, we are going to build it from nothing, not by memorizing formulas, by solving problems. Every single piece of this machine exists because someone had a specific problem, and this was the only way to fix it. By the end of this video, that tower won't look mysterious anymore. It will look inevitable. Before transformers, machines read text the same way a very tired person reads a very long book, one word at a time, left to right, never going back. Now imagine a bus. The bus stops at each word. The word boards and takes a seat, and the bus keeps moving. But this bus has a fixed number of seats, and it never turns anyone away. So when the seats start filling up, it compresses. Two previous words get squeezed into one seat. Their meanings get averaged together. Some detail disappears. This is not optional, but the next word has to board. For a short sentence, that's fine, barely any compression. But for a long sentence, by the time you reach the end of the sentence, the first word has been through many rounds of squeezing. What started as a rich, precise meaning is now a blurred smear averaged into something generic. So why does this problem matter? When the bus rolls to it, what does it refer to? The machine needs to know, trophy or suitcase. To find out, it looks back, but trophy boarded at stop 2, got compressed, got averaged into everything after. The signal is too faint, the machine guesses wrong, so there had to be a better way. Here's the hard question. How did you do that? You didn't follow a fixed rule. You looked at the whole sentence all at once and let every word inform every other word. The meaning of it depends on context, and context is everything. The bus could never do that. By the time it rolled to it, the word trophy was already a compressed smear. Imagine if a machine could do the same processing every word simultaneously to decide which ones matter most through a learnable process called attention. This mathematical mechanism for measuring relevance was the core of the 2017 paper, Attention is All You Need. It wasn't just a bold title, it was a claim that changed everything. So how, exactly, does a word look at another word? Let's make it concrete. Look at how the input sequence transforms. The words flow like particles through a tube. Then the stream forks into 3 branches, each carrying a different color of particles. One branch carries the query sequence, what each word is looking for. Another carries the key sequence, what each word broadcasts about itself. The third carries the value sequence, the actual content ready to be shared. 3 sequences working together, all derived from one. This is called self-attention, a sequence attending to itself. Imagine a flat, square plate with a grid of holes, one hole for each word pair. On one side of the plate sits the query word. On the other side, every other word lines up as keys. This grid of holes is the similarity matrix, a visual map of every word's relationship to every other word. Take the query it as an example. Each word at this point isn't just a letter, it's a list of numbers, learned from billions of sentences. Picture a bar chart, dozens of bars, each one encoding something about how that word is used. It has its bar chart, and trophy has one too. Place them side by side. The same bars are tall, the same bars are short, so they match. The hole at trophy opens wide. Now place it next to the. They're completely different. The bars share no common height, almost no overlap. The hole at the stays nearly shut. The plate compares them and determines the size of each hole. High similarity, big hole. Low similarity, tiny hole. Now we examine the hole stream's relation, how values flow through each hole based on the query key matching. Take the word it as an example. Because it and trophy have a high relation, they get a big hole, allowing more value to flow through from trophy. Because it and the have a low relation, they get a small hole, barely allowing any value flow from the. Look at them side by side, a big hole with a thick stream versus a small hole with a thin trickle. We see these streams flowing separately towards the plate. At the bottom, these separate streams from all words converge and merge together into one unified output, leading to the transformed it. These attention weights act as filters relevant words pass through easily, while irrelevant ones are suppressed. Each value stream is scaled by its importance, creating a weighted blend of information. The result is a richer representation that captures the contextual meaning of our target word. So far, we've watched words find each other comparing signals, weighting scores, blending meaning. But here's something we've been quietly skipping. Trophy, suitcase, it. These are symbols, letters in a sequence. A machine cannot add two letters together. It cannot measure how close king is to crown. Before any of that attention math can even run, there's a problem hiding in plain sight. These words need to become numbers first. Proper numbers. Representations the machine can actually calculate with. Every word has a slot in a lookup table inside the model called an embedding table. Each slot holds hundreds of values, encoding everything the model has learned about how that word is used across billions of sentences. Words that appear in similar contexts end up with similar slots. King and queen land close together. Stone and rock cluster nearby. Meaning becomes geometry, what we call a token. When a word enters the model, it finds its slot, pulls out its numbers, and converts to a representation token. That's the moment a word transforms from a symbol into something the machine can work with. With meaning now mapped as geometry, attention sifts through those numbers. Every word scans the others, gathering context. Our it receives a seasoned blend of trophy and suitcase. This is like kitchen prep. We've gathered the ingredients and chopped them up, but the actual cooking hasn't started yet. Now, the stove finally turns on. This seasoned blend of trophy and suitcase, the result of all that prep work, is the ingredient entering the feed-forward network. The first layer expands this mixture into a space 4 times wider, like spreading it out across a hot pan. Hundreds of features are tested for a match. Only the features relevant to this specific blend start to sizzle and fire. Then, the second layer compresses those active signals back down to its original size. This forces a synthesis, turning those raw ingredients into a single, refined concept. The representation exits transformed by the heat of its own internal processing, that is, reasoning. The division of labor is now clear. Attention moves information between words to prep the dish. The feed-forward network cooks that information. One communicates, the other thinks. And they alternate, layer after layer. But here's a problem you'd only discover by actually building transformer models with many stacked layers and watching training break down. Every attention pass shifts numbers. Every feed-forward pass shifts them again. Stack 96 layers of compounding shifts, and some values explode toward infinity, while others collapse toward zero. Training falls apart, the model drifts into chaos. The fix is unglamorous, but essential. After each step, a normalization pass snaps all values back to a consistent scale. No information is lost, just the magnitude stabilized. It's the difference between a clean signal and static. Now we can put it all together. One transformer block is normalize, then attention, then normalize again, then feed forward. These are the core components we've built to address each specific problem we encountered. This is the fundamental building block of the entire transformer architecture. Each transformer block has multiple layers, and when you stack 96 of them together, you get the immense depth of GPT-3. The input enters at the left side as raw numbers, representing tokens and embeddings. The output tokens emerge at the right side as deeply refined encodings of meaning, the result of 96 rounds of communication and processing. That tower in the opening? Now you know every brick. Let's go back to where we started. Is the machine thinking the way we do? No, not exactly. But it is doing something extraordinary, extracting meaning from patterns at a scale and precision that was, until very recently, completely impossible. So is it just predicting the next word? Technically, yes, that's exactly what it's doing. But look at what it built to do it. Attention is all you need. They were right.